Welcome to the deep dive. Today, we're really wrestling with a question that keeps a lot of people up at night. Can you actually predict cryptocurrency prices?
It's the million-dollar question, isn't it? Or maybe the million Bitcoin question.
Yeah, exactly. And we're tackling it by, cracking open a specific piece of research, a paper from Politecnico di Milano called Quantifying Cryptocurrency Unpredictability, a comprehensive study of complexity and forecasting.
That's right. So our goal in this deep dive isn't to, add to the speculation, but to really strip away the hype and just look at what this specific paper says the data tells us.
Okay, so what do crypto price movements look like when you analyze them purely on their own? Just the past prices.
Exactly. Just the historical data.
Hmm.
And then do those really complex forecasting models, the ones everyone assumes you need for crypto, actually perform better than, well, simpler ones? In this specific univariate context, as they call it.
Right, univariate meaning just looking at the price history by itself, no outside info.
Precisely. And the paper really digs into this assumption. You'd think more data, more complex algorithm,
Yeah.
better prediction, right?
Yeah, that's the intuitive thought. But this paper tests that hard.
They look specifically at 5 major cryptos: Litecoin, Binance Coin, Bitcoin, Ethereum, and XRP, using daily prices.
Okay, and what was the time frame?
They use data from July 3rd, 2020, right up to December 21st, 2023. So a decent chunk of recent history.
Got it. Okay, so let's dive in. They started by looking at the kind of the inherent nature of this price data, right? Its complexity.
Yes, exactly.
Yeah.
Before even trying to predict, they asked,
Mm-hmm.
what are we dealing with here? Is there structure? Is it just random?
How do you even measure that?
Well, they used a few sophisticated techniques, things like permutation entropy and something called Jensen-Shannon complexity.
Okay.
They've visualized these on what's known as a complexity entropy plane, or CH plane. It's basically a map to see where time series fall in terms of randomness versus structure.
A map of randomness. And where did the cryptos land on this map?
This is where it gets really interesting. All of them, Bitcoin, Ethereum, the others, consistently landed in the lower right corner of this plot.
Lower right corner. Okay, translate that for us. What does that mean?
That means 2 things are happening at once. First, high permutation entropy. That's a strong signal of randomness. Think of it like short price patterns rarely repeat predictably.
Okay, lots of randoms.
And second, low statistical complexity, which means there's not much discernible underlying structure or pattern within that randomness for a model to learn from.
High randomness, low structure. That sounds an awful lot like, well, noise.
Exactly. You nailed it. And the paper explicitly points this out. They showed these cryptos sit right on a line on that CH plane that characterizes different kinds of colored noise.
Colored noises like white noise
Or
or...
Brownian motion, yeah. Think of that totally random jiggling of a particle in water. That's Brownian motion.
Right, I remember that from physics. It's a classic example of randomness.
It really is.
Hmm.
And it's often used as a benchmark for randomness in financial time series analysis. So the paper didn't just eyeball it on the graph.
They quantified it.
Yes, they used another measure, the permutation Jensen-Shannon distance. It basically calculates how statistically close the crypto data is to different known noise types.
And what was the verdict? Closest to...
For most of them, Bitcoin, Ethereum, Litecoin, Binance Coin, the statistical properties were closest to Brownian noise. That's sometimes called 1F2 noise.
Interesting. You said most of them.
Yeah, XRP was a slight outlier. It was actually a bit closer statistically to what's called pink noise, or 1F noise. Still noisy, but slightly different character.
Okay, mostly like Brownian motion. Did it matter how much data they looked at? Like the whole 3 years versus shorter periods?
Good question. They checked that too. They reran the analysis using data windows of 1 year and even just 6 months.
And did the picture change?
It did, and in a way that actually reinforces the randomness idea. As the time window got shorter, the cryptos on that CH plane moved even closer to the characteristics of pure white noise.
White noise, like TV static. That's even more random, right? Less structure than Brownian motion.
Exactly. It suggests that, especially in the shorter term, the crypto price movements become even more unpredictable, losing even the slight statistical dependencies you might find in Brownian motion. It looks increasingly like just patternless chaos.
Wow. Okay. And they had another analysis method too, something about frequencies. Power spectral density.
Right, PSD.
Yeah.
That looks at the data from a different angle in the frequency domain.
Yeah.
It basically asks how much power or variance is there at different fluctuation speeds.
Did it agree with the noise idea?
It did. The PSD plot showed the crypto data followed a power law distribution very similar to Brownian noise. And importantly, this held up whether they looked at the full 3 years or the shorter 6-month window.
Okay, so let's try to synthesize this complexity part. The big takeaway seems to be if you only look at the past prices of these major cryptocurrencies, the data itself behaves, statistically speaking, a whole lot like random noise, specifically like Brownian motion,
That's the gist of it. High randomness, very little discernible structure or pattern.
which leads directly to the next big question they tackled, right? If the data looks like noise.
Can you actually predict it? How well do forecasting models fare when you feed them this apparently noisy data?
Yeah, this is where the rubber meets the road. Did they test different kinds of models?
Oh yeah, they threw the kitchen sink at it. They used a whole range.
Mm.
From like really simple statistical methods,
Like what?
things called naive methods, basically just assuming the next price is the same as the last or follows the recent trend.
No.
Also classic time series models like ARIMA, ETS,
Mm.
stuff statisticians have used for decades.
Okay, the classics. And then the more complex stuff.
Definitely. They included machine learning models, random forest, XGBoost, and several deep learning models like vanilla recurrent neural networks, RNNs, LSTMs, which are popular for sequences, and another one called NBeats.
So a real spectrum from simple to very complex. How did they test them fairly?
They used those same time windows for training 3 years, 1 year, 6 months, and they tried predicting different distances into the future. Just 1 day ahead, 7 days, and 30 days.
And the success metric was.
Mean absolute percentage error, or MPE. Lower MPE means the prediction was closer to the actual price, so lower is better.
Okay, the moment of truth. What was the main finding? Who won?
This is probably the most surprising result in the paper. Across nearly all the different scenarios, different coins, different time windows, different forecast horizons, the statistical models consistently outperform the machine learning and deep learning models.
Wait, really? The simpler models beat the complex ones?
Pretty much, yeah. It's counterintuitive, right? You'd think MLDL models designed to find complex patterns would shine here.
Absolutely. Especially for something people think is complex, like crypto. But the paper says no, at least not when you only use past prices.
Exactly. And it gets even more interesting. It wasn't just the statistical models in general won.
Go on.
Even among the statistical methods, the really simple ones, like naive drift and naive seasonal, performed just as well as, or statistically couldn't be distinguished from the more sophisticated statistical models like AutoArima or AutoETS.
No way. So just assuming the price drifts like it did recently was basically as good as a complex statistical model.
In many cases, yes, statistically speaking, simplicity really held its own, which is quite a finding.
So simple statistical models were the winners. What about the models that did poorly?
Well, Profit, which is another statistical model from Facebook, actually did much worse than the others.
Why was that?
The paper suggests it's because Profit is specifically designed for time series with strong seasonal patterns and holiday effects, like retail sales. Crypto data doesn't really have that kind of structure.
Makes sense. And the big complex models, the ML and DL ones.
Many of them struggle significantly. The paper points out that for models like the vanilla N and LSTM, the prediction error, the MAPE, actually got worse when they had less training data, like using the 6-month window instead of the 3-year one.
So they needed lots of data, but even then, they didn't beat the simple stuff. And they struggled more when the data looked even more like white noise.
That seems to be the implication. They couldn't find reliable patterns, especially in the shorter, noisier data. The NBeats deep learning model was noted as being more competitive, but still didn't statistically outperform the best simple statistical models consistently across all tests.
Okay, so summing up the forecasting part. If you're only using past price data for these cryptos, complex ML and DL models don't seem to offer an advantage. In fact, simple statistical models, even naive ones, work surprisingly well, or at least aren't significantly worse.
That's the core message from the forecasting analysis. It really challenges the more complexity is always better assumption in this context.
Right, so let's tie these two big pieces together now. Part 1. The complexity analysis shows crypto price history looks a lot like random noise, like Brownian motion.
Yep, high randomness, low structure.
Part 2. The forecasting results show simple models work best, complex models struggle.
Exactly. And the connection seems pretty direct, doesn't it?
It really does. The complexity findings basically explain the forecasting results, if the data fundamentally looks like random noise.
Then trying to fit a complex model to find intricate patterns is likely futile, because those patterns just aren't consistently there in the first place, at least not in a way these models could capture from price alone. A simple model that just follows the recent trend, like Brownian motion does, ends up being hard to beat.
So the paper's overall conclusion is essentially that trying to predict crypto prices based only on their past performance is incredibly difficult, maybe even fundamentally unfeasible, because it's like trying to predict noise.
That's the strong suggestion. The resemblance to Brownian motion and even white noise in shorter windows makes purely historical univariate forecasting look pretty bleak, according to this study.
Okay, so if looking only at past prices is so tough, does the paper offer any potential ways forward, any glimmers of hope for better prediction?
If it does offer a suggestion, yeah. It points towards incorporating additional covariates.
So variates. Okay, meaning bringing other kinds of data into the mix, not just the price history.
Exactly. They talk about two types. First, past covariates. This can be things like technical indicators, RSI, mass CD, which are themselves derived from past prices but maybe capture different aspects,
Hmm.
or maybe data from other assets that might be correlated, like, say, stock indices or other crypto prices.
The idea being these might help filter the noise or provide some context.
Potentially, yeah. They might help the model find slightly better signals amidst the randomness.
Okay, that's past covariates. What was the other type?
Future covariates. This
Future.
is information about things we know or expect will happen in the future.
Like what?
Maybe scheduled events like Bitcoin halving, major network upgrades for Ethereum, known regulatory decision dates, or even forecasts of macroeconomic indicators like inflation or interest rates.
So trying to anticipate external shocks or influences that aren't reflected in the past price alone.
Precisely. But, as the paper also points out, these future covariates have their own issues.
I can imagine, like what?
Well, first, getting reliable future information is hard. And if the future covariate is itself a forecast, like an economic forecast, then you're just adding another layer of uncertainty into your prediction model. It's not a magic bullet.
Right, predicting the predictor. Okay, this has been a fascinating deep dive into this specific paper. So let's try to boil down the core takeaway for you, our listener, based on this research.
Based purely on this univariate analysis in the paper.
All right. Trying to predict cryptocurrency prices using only their own past price data seems incredibly difficult. Why? Because that data looks and behaves statistically very much like random noise, specifically Brownian motion.
And maybe even more like pure rain noise over shorter periods.
And counterintuitively, maybe the biggest surprise is that simple, classic statistical forecasting methods appear to work just as well as, or sometimes even better than, sophisticated machine learning and deep learning models in this specific context.
It really highlights the challenge. If there aren't strong, learnable patterns in the historical price data itself, complex models don't have much to grab onto.
So it leaves us with a pretty interesting thought. If complex models and just looking at the price history aren't the answer, according to this study, what specific types of external information, those covariates the paper mentioned, do you think would actually be the most valuable? And maybe more importantly, the most reliable for potentially making better crypto predictions?
That's definitely something to chew on. What data truly matters, and can we trust it?
Indeed. Well, thanks for joining us for this deep dive.